Abaqus. We're going to give you a brief introduction. I'm going to cover some of the capabilities of Abaqus, and then Tim is going to talk about what's new in Abaqus 2017, as well as go through some of this problem setup and show you how Contact can be used. So in introduction, SIMULIA is the Dassault Systems brand dedicated to making realistic simulation an integral business practice to explore, discover, understand, and improve product life and nature. I'm not sure if you've seen some of their commercials, but they go well beyond mechanical design. They want to really solve some of the tough problems facing the entire Earth at the environment level, at the level of integrating with nature. So it's really robust offering that they're putting together. And they've done that over a number of years. So for those of you who've used Solidworks simulation, that was a Dassault Systems acquisition back in 2001. They've bought a company called SRAC, turned it into Cosmos first, and then it became Solidworks Simulation. A few years later, in 2005, they bought Abaqus. And Abaqus, of course, is the cornerstone of what we're going to talk about today, but it's the cornerstone of the SIMULIA brand. It really is what helps them do this. Since then, they've bought a few more companies that add to that brand. We're not going to talk about them today, but EyeSight is a design automation tool that gives you the ability to test the robustness of your tools and to explore your design space. Tosca is a non-parametric optimizer for topology optimization. FESafe is a really robust fatigue and durability tool that goes well beyond the capabilities that you're familiar with in SolidWorks simulation. There's also SimPo, which on the SolidWorks side is SolidWorks Plastics, SFE, Greensoft, and Dymola, and even SimPack has been added to their tool set. Now, to be clear, we do believe in SolidWorks simulation. It has a number of advantages. It is the design validation for all SolidWorks users, meaning people who aren't necessarily going to be analysts. It's really powerful but easy to use, and it has that short learning curve. Perhaps more importantly, it's integrated within SolidWorks, so you never leave that environment. You don't have to go in and out, which means that you can do a lot of what-if design scenarios to figure out what if this design A, B, or C is better than D? And that's the real strength of the tool. So it is by far the most efficient way to perform simulation for the SolidWorks user. Now the tool sets that we've sold on that capacity from the FEA perspective handle static analysis, motion simulation, modal analysis, a thermal approach to FEA, drop test, high cycle fatigue based on stress cycles, optimization, pressure vessel, and then simulation premium. We have the ability to go into nonlinear range to do harmonics and dynamics and random vibration, and we can also do some composite capability here. But we have a number of customers who need to go beyond that, and that's why we brought on SIMULIA Abaqus a few years ago, and it solves these types of problems with two solvers, a standard implicit solver and an explicit solver for highly dynamic events. By going this direction, you do get more complex, but you also increase your ability to solve tougher problems and to increase the realism of the type of results that you're going to get. Now, I mentioned that SIMULIA Abaqus is the foundation of the SIMULIA brand. It is the most powerful, complete solution for both routine and sophisticated engineering problems across the full spectrum. It handles both linear and nonlinear FEA, implicit and explicit dynamics. It has great contact feature, can handle fracture, composites, and it can do co-simulation with other tools like CD Adapco for CFD. Now, some of the problems that people do with SIMULIA Abaqus start at the designer level. They might actually be fairly simple and things that you could even approach in SolidWorks simulation, but perhaps you're going to get more accurate results depending on the types of materials that you choose. But people will use SIMULIA Abaqus for these entry-level problems all the way through complicated things like the BMW virtual crash test. These are things that both Honda and BMW now, they don't even crash a car until they have to send it off to the NHTSA. They do all of this stuff virtually within SIMULIA Abaqus. Now the products are based into two types of solvers, the standard and the explicit. They both can handle nonlinear capabilities, and they are meant for production use, and they're based on the finite element method. And when you buy the tool or you lease the tool, it also comes with Abaqus CAE, which is the pre-post processor. CAE stands for Complete Abaqus Environment. Now, the standard tool is based on the implicit solution SEA technique, so it's intended for static and structural dynamic events. It can, as I mentioned, can handle linear and nonlinear behavior, but you see it's going to be a lot of the things that you might already be doing with SolidWorks simulation, like figuring out the bicycle frame stress, or whether or not you're going to be able to handle a clip insertion, or if your gasket's going to seal adequately. The explicit is where you really get into a different space, where you're looking at explicit time integration, so it's intended for high-speed transient dynamic events and highly nonlinear quasi-static events. And this is where a lot of these things start to come in as to why you would look at Abaqus instead, because there's certainly capabilities that go well beyond the zone of what SolidWorks simulation can do. Now, there's also some advanced multiphysics capability. So within these standard and explicit solvers, you'll find the abilities to use things like coupled Euler-Lagrangian and smooth particle hydrodynamic approaches to how fluids move to enable fluid structural interaction. You also find thermal capabilities, electromagnetics, and acoustics within these tools to couple multiphysics things together so that you can get a better understanding of what's happening. Now, that's going to give you the realistic simulation that you're looking for, but it's also very important that you have a robust tool that can handle very complicated things, complicated actions, and complicated contact, like with the collapse of this Jenga tower, something that would be impossible to handle with SolidWorks simulation, but that's actually really easy to set up inside of SIMULIA Abaqus. Similarly speaking, large deformations. These are things SolidWorks simulation cannot predict, but Abaqus can handle it well, so it understands the changing contact conditions as that deformation is happening. It also can be used if adhesives and delamination are a part of what you're looking for and needing to understand if you're going to have failures. And it can handle a wide range of materials and mesh models. So whereas SolidWorks simulation gives you a certain set of materials and a certain number of things that you can do with it, Abaqus actually gives you a large number of material models, meaning that these are the way that these materials are going to behave under a given event. You enter the data for the material that you're going to use, which means that you're going to be working with a material model that is going to exactly match what's happening in the real world. And if it's not there, Abaqus gives you the tools to create those material models yourself. Now, the complex contact is extremely robust. We just showed you the Jenga tower, but some other things that you may not have been able to experience before. This wire crimping, as simple as it is, it's a problem that I know SolidWorks simulation can't do and that people need to do in a number of situations. Now, it's very accurate, as you can see from the collapse of this tower, and taking a look at it compared to the realistic simulation. The same thing happens with the BMW crash test, and we have a picture of that later. But these things all come together to give you that realistic simulation, including what happens if you start having damage and fracture analysis. Do you have materials start to break away? So this can be very, very important in understanding in things like a bird strike against an airplane. So you can get the progressive damage with fibers. You can get crack propagation. Well, first of all, understanding whether or not it is going to propagate at all, and if it does, which direction is it going to go, and whether or not you can have delamination. I'm sorry that my video is not working here, but the delamination of this assembly, it would show how it would separate as it moves forward throughout the event. Now, I mentioned the complex material behavior. Now, it has a lot of built-in things for metals, rubbers, and composites to handle either linear, nonlinear, elasticity, and plasticity, certainly isotropic and anisotropic, rate and temperature dependence, but it also includes additional materials and models like soils and rocks, concrete and ceramics, paste and polymers, human body tissue. This allows you to do your simulations more realistic to the world around you instead of just thinking about, you know, metal and aluminum and how those things work together. So this realistic simulation, it does depend on these advanced material models to eliminate assumptions. The more accuracy you put into the material model, the more realism that you're going to get out of your solution. And you can kind of see that in some of these pictures here, where the model looks exactly like the test results that were filmed. This also allows you to integrate many types of physics, so if they have an impact on how those results are going to look in the real world, you can incorporate them into your study. So in summary, what kind of problems can benefit from Abaqus? If you've got very large distortions, if you've got large numbers of rapidly changing contact interactions, if you have complex material models that go beyond SolidWorks simulation capabilities, or frankly, if you're using composites beyond the very simple structures. If you need to do load sequencing, or if you need to do rigid body motion plus deformable parts, it's very likely that SIMULIA Abaqus is probably going to be a better solution, give you more accurate results, give you a realistic simulation before you ever have to build anything, so that of course you can make better design decisions before you start money creating prototypes. That said, I'm going to transfer this over to Tim, and he's going to show you a little bit of the interface.
All right, thanks for that, Glenn. I'll go ahead and request control. And I'm going to start out with what's new in Abaqus 2017. Bear with me a second here. So starting out with what's hot off the press, I'm going to go through a lot of these enhancements just sort of quickly, and then I'm going to dive into a little more detail by showing a couple problems that use these particular enhancements in Abaqus. The mile-high summary is that we've had a lot of enhancement to the contact and constraint controls. There's been some research put into the extended finite element fracture mechanics models in Abaqus Standard, and they've introduced a new feature called a linear complementary problem equation solver in Abaqus Standard, which basically linearizes contacts within small displacements like you may see in a ball bearing to reduce your computational cost there. And research has gone into the C-zone composite damage models per Explicit and a few other key functions like the Abaqus plugin for welding and additive manufacturing. And another key one, which is a usability enhancement that allows you to control displacements through space and time. So rather than controlling a displacement with a load increment, you can describe a three-dimensional path through time. So that's a key one. So a major measure of the FEA tool improvement is the sparse solver performance, and this one has gotten steady development. The short of it is from version 6.12 to today, we've seen a 20% improvement for the larger engine block assembly on the left, and a 27% improvement for the flywheel assembly on the right. The LCP equation solver is a development that allows us to look at contacts without any sliding contact in a new solver to Abaqus CAE, and what this offers is if we have a small set of contacts, we see a 10x improvement in the computational time. The type of problem that this would be useful for is something like a bearing set where you have, somewhere around 10 contacts and you want to do linear load perturbations. You can solve for your your material nonlinearity in a base case, and you can do other steps around this in a linear perturbation. So you take advantage of having built the main stiffness matrix and solving some quick steps around it. So I want to introduce the Abaqus and SolidWorks associative interface. So the way I'm going to do that is to take you through a can crush example. We have this. We have a pretty simple model, which is 3 parts: a floor, a can, and a top that's going to deform it. So now I'm going to go into SolidWorks and show you this assembly. So to use the SolidWorks associative interface, I'm going to trigger the Abaqus export here. First, I'll go into Abaqus and we'll switch into the model where we're going to pull it in. We have a tree format in Abaqus, sort of like SolidWorks, where we have a drop-down menu where we can get at our parts, material properties, the assembly, where those parts are called instances, and our load steps. And load steps are key because it determines the type of analysis you're going to do. So with that, I will send this model over to Abaqus, and you can see we've got our same basic assembly: floor, a crush, lid, and the can. So I've gone through this problem a bit ahead of time, and I want to take advantage of that by copying some of my material definitions, sections, and the contact properties from my setup can model into my new model. So it's pretty simple. We go through and we pick the material properties and things we want to populate. if I want to come in and take a look at what those material properties are, in the property module, I have a material manager. Looking in here, it's a very simple linear elastic material model. Since I'm using explicit dynamic step, we need to define a density. So one of the things we have a capability to do here is we can import test data, and there's a plugin where we can pull out our elastic modulus and our elastic plastic curve. We have some similar capabilities if we have stress strain data for a plastic model. There is a way to evaluate which material models fit that best. And we have quite a few options around ductile damage or quite a few ways that we can either make a material fail or enhance the plasticity look. But for this one, we'll stick with a simple linear elastic material model. So the next thing to do, I've copied a section over, which is a section defines the type of element. So I've said we want a simple shell model, and then we will apply that section to the CAM, and we're set there. So if we want to look at the mesh of this piece, I'll turn the mesh view on, and you can see we want to take a pretty fine resolution for the way that we mesh this, because we want to capture some of the the local buckling in this. If we look at the overall assembly, you'll also notice that we have a fairly coarse mesh for these rigid plates that are driving to crush the can. They're of less concern, so we don't detail the model as much in those places. So once we define our material model and we put a mesh to it, we're going to come in and take a look at the step we do. So I have a 0.2 second explicit dynamic step. We have some options for mass scaling. You can run those as default, and the main effect there is your model is going to run a bit longer, but I did scale this one to get a 1e to the minus 6 load or step increment. One of the things that this does is allow you to solve an explicit model with a lot more speed. You do need to watch that you're not introducing mass effects that sort of take over the solution of this problem. So now I'm going to come down to the loads and boundary conditions step. We have a boundary condition manager. One of the things we can do here is we can turn boundary conditions off either at any certain step, or we can create one load scenario that uses them and copy that model and turn them off. The boundary conditions are very simple. The bottom rigid plate has all 6 degrees of freedom constrained, and the top rigid plate deforms about 2 inches with an amplitude scale factor. We have some controls around what type of amplitude we want, whether we use a smooth step or a tabular, a simple linear application of those. The particular type that I use here was just a linear ramp. So with that, we're ready to switch on to contact. So contact for this one's pretty simple. I use the general contact explicit. So I came in, I create an interaction, and I detect all contact with self. We do have friction in our analysis, and we have some more controls in the contact setting itself where we can define tangential behaviors, or we could simply run with the default. We also have the capability to use cohesion, which I'll cover a little more in a later example problem. So with that, we've set everything we need to come down and submit a job. So if I was going to run this right now, I would just create a new job by creating and writing an input, but I solved this one ahead of time, so I'm going to go ahead to visualization where we can see what that looks like in the post processor. So here, the default, if we just plot the finite element model, is everything in the same color. We have some controls there. If we want the parts visualized in a different color, we can do that. And if I animate the time history of the deformed results, you can see the sort of the real-time view of that as it runs. We have some capabilities to save that to an AVI file if we want to save that out. or we can do the same type of a plot with a stress time history. I did use a linear elastic model, so it's kind of a crude approximation, but we'll see some higher peak stresses than are realistic. But you can definitely hone that in if you have test data that you want to apply to your model as well. We have some capabilities to watch things like the energies if we want to make sure that we aren't exaggerating the inertial effects with our mass scaling. The red line that you see here is the internal energy, and the blue line is the kinetic energy. And I think the rule of thumb is somewhere 2 to 5% if you're doing a quasi-static problem like I am right now, that you're in the ballpark and you're okay there. So that's a quick introduction to the tree layout of the Abaqus menu settings, and a quick example of how to mesh a problem. So I'm going to come back to go on a little bit more into the enhancements in Abaqus. So first, a broad set of definitions of what goes into general contact. We have edge to surface, edge to edge, and a solid or shell edge to another surface, and a beam edge to surface. So some of these animations highlight, what those type of contacts look like. In the bottom left, we have beam to beam. That's a type of contact that can have some novel applications. If you want to guide something through time and space, you could configure a beam with another beam around it that defines a complicated path that you want a thing to travel, if you'd rather do that than describing it with equations. So what's new in general contact beyond these basic capabilities is now we can define the beams as the master in a contact set. So just to give us a little more flexibility around things we can do between beam and solid elements. And towards that, I've got another quick example problem here where I'm going to show you a visualization of that, where we have a gear, and right now the beam profile is not rendered, but if I render that, you'll see that those, the beams have a cross section. We have the capability to scale that if we want them to appear smaller than they actually are. But I'll just go ahead and render them at full size. So this one is a contact analysis where the first gear drives the chain, and by association the second gear. And so a very similar setup. We use general contact here, and we put these beam elements in contact with the chain. Nice thing about this is it's a pretty, it's a light on setup for what can be a very complicated problem. You have the capability to come into this and take these beam loads into a submodel if you want a fully detailed model of the chain assembly. But if your real focus is around the gear, the interaction of a gear and a hub, you may be happy with a very computationally light rendering of that part of the assembly, and that's what this one highlights. So here is just another animation of those two side by side. And the last piece of this that I wanted to touch on was we have some new control around cohesive behavior in general contact. So what that means is that we can have a general contact model where we have certain elements with damage parameters, whether it's stress or energy. So that allows you to do things like have some parts stick to each other and not others. If you want to delve further into the behavior inside composites, we can have the fibers have a cohesion strength with the matrix. Or if we just want to build a model like you see in the bottom left of what's like a brick wall, where all these where each individual part has a bond strength with the other parts, but doesn't need any continuity in the modeling. So one area that this could be key is if you want to pull in a finite element model from another code where they're all separate in nodes. If you don't want to merge them for whatever reason, you can use that. And I have an example that I want to go through here, which is I've set up a wall with a ball impacting it. And these are all built with that cohesive modeling and general contact. Key differences of this analysis with the other analysis I walk you through is that we're going to have an initial condition of velocity around the ball, and that we got the cohesive contact between the bricks. Again, the brick wall is an explicit dynamic analysis. This one I run a bit longer than the can for a half a second, so we can see what happens when that ball gets further out and bounces. Another thing I'd point out is that there's no mass scaling in this one since we are considering a highly dynamic event. I didn't want to add any inertial effects, and it's a relatively large element, so that wasn't too much of a concern. If I turn the mesh off, you can see that we have some layers of different types of bricks. We have a few half bricks at the end, and otherwise the bulk of the structure is built on the whole red bricks. So our step type is an explicit dynamic. If we look at our material models, I have a really simple material model, which is just a brick, and it's a linear elastic. We use a modeling abstraction where the ball is a discrete rigid part. So what that means is we really only capture the mesh on the outside of the ball. And then if we go into the ball properties, we have a capability to just add a point mass and rotational inertia there. The units are in inches, so this one's really pretty heavy, somewhere on the order of 4,000 pounds. And then with that, the next step is really to take a look at what we do in the context. So we do have general contact defined where everything is detected in contact with itself. And then going a step further, not everything is in cohesive contact. So with that, I basically say the back of every brick halfway through the wall is bonded to the front of every other brick, or bottoms and tops are bonded. Otherwise, the ball is not bonded to the wall, so we want to put some amount of control in there rather than using complete default properties. And then if we look at the cohesive model, this is a fairly simple material model where we just have a certain stress triggers release of the cohesive element. And in the loading, this one is this one's pretty straightforward. Other than the bottom of the floor being constrained, the bottom of the bricks being constrained vertically, the floor is tied in all 6 degrees of freedom. And you can see here that I had one analysis set up where I had a ball spin constraint that the ball couldn't rotate, but I've got that disabled in this particular run. So I use the ability to trigger those on and off. And this is another one. I won't put you through watching it solve right now. I believe this one solves in about 15 minutes, but I'm going to skip over to the visualization. Again, I'll just turn on the coloring by part instances so we get a different color for all the different bricks. I'll go ahead and animate this one. So we can choose how many of our steps are active when we visualize these things. If we want the animation to go, real quick without a lot of resolution through time. Once it goes through mining the rendering data from the first pass of the output database, you can see that it shows the animation quite quickly. And if we want to come in and look at what some of these output parameters are, ahead of time I defined a parameter to track some of the spatial displacement of the ball and acceleration and velocity. So, probably not too surprisingly, I think the ball, I need to turn on my, the ball goes through a pretty significant change in direction when it hits the floor. Or if we plot the ball velocity as it goes through the wall, there's a very large reduction in speed while it's braking, and then it maintains basically consistent velocity once it's through the wall. So that's the conclusion of my showing of the new features in Abaqus 2017.